Welcome everybody. So as Martin said, I'm going to talk today about the .NET client for Elasticsearch and its codebase, for which I'm primarily responsible together with two of my great colleagues down in Australia. So who am I and why am I talking about my codebase on the JetBrains webinar? I'm a .NET developer for quite some time. I was initially I started to get a little bit frustrated with Visual Studio, so a couple of years ago I joined the OmniSharp project to create a better editor's experience for .NET. So I started the Atom plugin for OmniSharp, and I did the website and the logo. But as soon after Rider came along, and I jumped ship to Rider, and I've not looked back. I don't think I've opened Visual Studio in the past 2 years. I'm super happy with Rider, and so when this chance came along to talk about what it means to our code base and talk about my code base at the same time, I jumped on it. Sadly, I couldn't do it as part of the .NET Day, but here we are a couple of weeks after it, and I'm still talking about it. I also maintained the editor config .NET implementation, which is part of ReSharper and therefore also Rider. So there's a tiny little piece of me inside of Rider and ReSharper as well. So it's my little bit of a claim to fame. Furthermore, I work at Elastic. At Elastic, I'm responsible for the stack lead for all of the clients that we have, and making sure that people can connect to Elasticsearch from many different languages and have a good time. So with that, I'd like to talk about the Elasticsearch client. So obviously a client has to talk to whatever it's talking to server-wise, and it will get sending bits and sending bits back. And in this case, we're talking to Elasticsearch. Elasticsearch is a full text search engine that's distributed horizontally and as well. So it's great. It can serve many different use cases. It's great to serve terabytes and terabytes of metrics or logs, but it's also great for smaller data sets. If you have more catalog, for instance, a product catalog, you want to offer a search on your website. So the beauty of Elasticsearch is that you can run it on one node, and quite often one node is more than sufficient, especially if you run a simple web search implementation. But Elasticsearch also scales horizontally, so you can scale to 3 nodes, 5 nodes, 10 nodes, 100 nodes. We've seen higher clusters than that as well. And furthermore, you can give each node in that cluster a specific role. So this you can give certain nodes master node only, so they're only in charge of maintaining the cluster state, but they don't actually store any data on their disks. And furthermore, you can configure Elasticsearch to be in a hot and warm architecture where certain data lives on very beefy machines, and data that is not queried as often can live on the less physically strong machines. So the client has to also the client also has to take all of this into account. So the Elasticsearch client doesn't connect to one database. It actually connects to all of the Elasticsearch nodes in the cluster. And furthermore, it can and sometimes will take into account the different roles that a node can have. So which problems do the client actually solve for you? One is maintenance. Quite often, or obviously I should rephrase that, sometimes you have to upgrade the server. Sometimes you want to put more hardware, attach more hardware, better hardware to the machine itself, or upgrade an operating system. You'll have to take down a node, and so the client has to be resilient to that as well. So that if you take down that node, you don't actually have to inform all of the applications that use the client to not go to this URL to this node anymore. Furthermore, the client helps you with network issues. So anytime you hit any type of network snafu, whether that is between the client and the nodes, or the nodes themselves have a hiccup in between them, the client will help you recover from that. Unreachable nodes, for whatever reason a node becomes unreachable, maybe it was accidentally shut down or a network rule was updated. Yeah, and it also helps you with different topologies, so you can actually create clients that only talk to warm nodes and clients that only talk to cold nodes, for instance. So you can clearly separate the hot path and the cold path in your application. We also deal with failover strategies. So if a node goes down, we automatically reroute the request to the next node that we know is up and running. So the failure becomes opaque to the end user. And once we've seen that a node goes down, we won't use it for some time, but at some time in the future, we'll have to resurrect that node and retry it to see if the problem has resolved itself. So we'll deal with that as well. And furthermore, you can also configure the clients to do various different kinds of load balancing. Out of the box, all of the clients do round-robin load balancing, so you don't create any hotspots in your Elasticsearch cluster as well. So the clients do a lot more than just shifting bits back and forth, although that's a very important part of the client. We also have to deal with more distributed nature of the Elasticsearch itself as well. So yeah, with the clients team currently is a small team at Elastic, but we maintain quite a few different languages. So there's Java, JavaScript, .NET, PHP, Perl, Python, Ruby, and Go, and maybe more coming in the future as well. So definitely check out our jobs page if you're interested. But in this talk, I'll talk specifically only about the .NET client. The .NET client is actually two clients. So the Codebase actually ships with two clients. One is called Nest, and the other one is called Elasticsearch.net. Why that is, I'll cover in the next slides. We have roughly 10 million downloads. Last I checked, we were the 63rd most popular package on NuGet. That's not from Microsoft as well. Doesn't sound like much, but I'm super proud of that. I'm happy to boast about 63rd most popular. I think that's a nice spot to be in. The first commit was in 2010, so the client has been around for a long time. The Codebase has been around for a long time, and obviously has gone through many iterations as well during that time. And it's basically my side job that turned into my day job currently, which is always, I'm in a very nice spot. Yeah, Elasticsearch itself was started in 2010 as well, and yeah, it did a lot of things right from the get-go, and I jumped on it immediately as well. We currently have around 150 contributors over the past 9 years or so. Yeah, big thank you to everyone who's contributed in the past. Like the client would definitely not be anywhere near as good as it is today if it wasn't for all of those 150 people. So yeah, again, big thank you to everyone who's contributed in the past, and hopefully after this talk, maybe you'll contribute in the future. So we'll definitely appreciate any pull requests that we get in the future as well. So I mentioned we actually ship two clients. So when we talk about Elasticsearch clients, we do have a sort of a separation between high-level clients and low-level clients. What does this mean? A low-level client implements the full API of Elasticsearch, which currently has around 260 different API endpoints, and that number is only going to increase in the future as many new features will become available in the Elasticsearch. The low-level clients use low-level constructs to send over the wire. So for different languages, a low-level construct means different things. So for Python, it's hashes, and for Ruby, it's hashes, and for Python, it's objects, and for JavaScript, it's objects. And for the .NET client, we support byte arrays, streams, anonymous objects, and just any serializable object. The clients are extremely configurable. So I'll touch on that in a second as well. So you can compose a client. You should be able to compose a client in such a way that it does what you want it to and no more. The low-level clients are generated from a spec, and how much we can generate and what's available to us spec-wise, I'll touch in this webinar as well. Then we have high-level clients. They use the low-level client. It's also a one-to-one mapping of the API, but it's strongly typed, basically. Obviously, this gives a better developer experience if you're coming from a statically typed language. But currently, this is only available for .NET and Java. So the low-level and high-level client in .NET. Low-level is Elasticsearch.net. As I said before, it sends bytes, byte arrays. You can send a dynamic object, even anonymous object, or streams, and it's dependency-free. So it's a great candidate to be included, for instance, in logging frameworks or etc., because it doesn't come with any dependencies. And then the high-level client is Nest, which is a strongly typed interface to Elasticsearch. It ships you actually not one but two API syntaxes. So there's a Lambda-based API. Some might call it Fluent interface to Elasticsearch. And there's a more classical object initializer syntax, which I'll show in a second. There's also helpers for queries, so bitwise operators to help you compose very complex queries that are represented correctly to Elasticsearch as well. And then the high-level client also ships with many observable helpers that coordinate over many requests. So you can do a bulk index of millions and millions of records, and the helpers will take care of threading and concurrency and retrying and incremental retries as well. So this is a clear distinction between low and high level. One is functional and will work for many different use cases, and the high-level client is really geared towards a happy developer experience as well for your applications. So yeah, with that, I'd like to do a quick walkthrough of the bits we actually ship. So here I have just a regular program, and I'll initiate a low-level client. So this is enough to instantiate the client. Then we just do a search. And send an empty object is serializable. So as you see, this is very low level. So the string response basically gets the body from Elasticsearch and represents this as a string. You can also make it return a bytes response, and you get like bytes from Elasticsearch, etc., etc. So for now, I'll just showcase the string response. And I'll just write it out the console. So pressing F1 was not part of the talk. There we go. So if I now run this, and it's building. There we go. So if we look at the console output, we can see that we did a request to HTTP localhost 9200, even though we didn't specify that. It's just the default address for Elasticsearch, so it's also the default address of the parameterless constructor. And then we can see that the request was not captured because we serialized directly to the request stream, so there's no chance for us to capture it. And then the response, we can actually see the response because it's automatically deserialized it into string for you. Using the high-level client should be equally simple, which is going for the Elastic client, which lives in the Nest namespace. And if you want to do a search here, you can do high-level search by Coco. And then we say new search request. Just the lambda from lambda syntax first. So here, the search actually returns a search response of my POCO, where the client will map every search hit automatically to POCO. So if we run this, write it back to console. There we go. You can see, again, even though we're using the high-level client, we can still debug it the same way. And now we can see that we've still got a healthy response from the Elasticsearch node, but the request and response stream weren't captured because we write and read directly from the request and response streams. But you can, there's actually an instruction in there that how you can set it up. And so if you want to see it, you can hit settings. And say enable debug mode. And now if we want it, we should be able to see the request and response. Yeah, so now we can actually see the response as well, which is quite big. And so we can actually see the request is just an empty object, and the response is a full-blown Elasticsearch search response. And then if we actually look at the search response itself, it's just a fully typed object that has documents of which are high read-only connection of the myPOCO hits that are returned from the search as well. So this is a very quick overview of the two clients that we use. The nice thing is that the high-level client uses the low-level client, so you can actually call the low-level client from the high-level client and say search and then we have to say post a new serializable object, and it's basically the same thing as the line above, and they return the same object as well. So yeah, so the low-level client really ships with all of the connectivity bits that are needed to talk to Elasticsearch, and the high-level client extends this with strongly typed request responses and helpers, more helpers to use against with Elasticsearch. So the client is basically built up out of internally with a I transport and an I connection. And both of them have a very simple contract. Basically, they request a T, and they get returned a T as well. And the same thing happens for I connection. It requests a T, either synchronously or asynchronously, and returns a T as well. So why do we ship with two interfaces that have the same contract? This is key to allow us to inject our smart connectivity bits, but still have the client itself dumb enough that if you don't want any of our smart connectivity bits, you can create a transport implementations that does nothing but kind of call Elasticsearch as well. Because if we actually go through a request into Elasticsearch, it's quite a complex flow diagram that we have to walk through to provide all of the fail-safe guarantees that I mentioned earlier. So, as highlighted by the animation, we do a client call, and we check, is this the first time we use it? Is the cluster state still? Select a node from the pool. Does this node need pinging? Yes, it needs pinging, so let's do a ping first. Okay, node is up and running. Let's call Elasticsearch without a valid response. And then, in the case of the valid response, we mark the node as stable, and we get back returned a success. So we only see one green box here, which is the success response, but there's a lot of red boxes on this flow diagram as well, which are all possible ways in which you can get returned a bad response from Elasticsearch. Either the sniffing field, which sniffing is a mechanism that we use to call out into Elasticsearch and find out which nodes are part of the cluster. You can have a bad ping, the response can be invalid itself, there's timeouts, max retries, exit points as well. So it's quite a complex scheme to actually perform a call into Elasticsearch with the .NET client or any client, because all of the clients provide these fail-safe mechanisms. And so the transport that we ship with, and I can show you this in the code as well. So if I show my transport itself, it's a lightweight interface. Request async. If you look at the actual transport implementation, it's a little bit more involved. And you can see the first thing it actually does is create a new request pipeline. And the request pipeline models our flow diagram very narrowly. And so first thing we do ask from the flow diagram is this the first time we actually call Elasticsearch, which is part of the diagram as well, highlighted by the second step in the diagram. And then if we go further down the code, we actually see, okay, we'll select the node, which is another step in the flow diagram. And then what we try to call if the sniffing information if the cluster information that we have is still, it means it's been too long since we've done a sniff, then we'll call sniffing. We optionally try to ping the node if the node needs pinging, meaning if previously the node was returning a bad response, we'll try to ping the node before we actually call Elasticsearch. The reason we do that is because the ping is configured with much smaller timeouts than an actual call into Elasticsearch is. So the ping is expected to feel faster than, for instance, possibly slow search or long index processes. So it's a way for the client to feel fast. And so when I talked earlier about that we retry on if something bad happens, we retry immediately. We won't back off and retry later. The clients are built to feel fast. Yeah. So if we go back into how we compose our clients itself, you can actually configure all of these steps as well. So for instance, we can say disable pinging altogether, and now the client will never do any pings. We can disable the sniff on startup, and I will never do the sniff the first time the client is used. Or we can give the sniff a different lifespan. By default, the sniffing information goes still after 30 minutes, but you can configure it, do anything that you might want. Yeah. So again, the clients should be really composable and configurable to do just as much as you need it to as well. So yeah, so as you see, in this simplified diagram, the transport will try to do a ping, sniff, or retry, and the request pipeline actually implements those options, and we'll select the node from the connection pool, and then we'll try the HTTP connection, which is the HTTP client-based iConnection implementation that we ship with, and then call Elasticsearch. So many different parts of the clients are injectable. By default, you can inject a custom iTransport, a custom iConnection, but also a custom iConnection pool, iRequest pipeline factory, iDatetime provider. So I'll get to why that's really helpful in a second. Also an iMemory stream factory. So by default, we'll use the pooled memory streams to actually run our to shares as much memory as we can when actually calling the Elasticsearch itself. And then you can inject a custom Elasticsearch serializer. And there's some asterisks there. These are the components that you can inject in the low-level client. And the same is true for the high-level client. But it also allows you to inject an Elasticsearch serializer, which is the same dependency as the low-level client, but used slightly different, which I'll touch on in the next slide. And an iProperty mapping provider. So why is the Elasticsearch serializer slightly different for the high-level client than it is for the low-level client? For that, I need to give you a bit of history as to how serialization used to work in the client. With in our 5.x version, so we're currently at 7.x, we used one serializer for the whole request and response. And in the low-level client, we used simple JSON, primarily because it's an easy, dependency-free JSON serializer that was easily embeddable. And the high-level client used JSON.NET. The problems with this were twofold. One was that JSON.NET allows you to specify static configuration. So if somebody specifies that types should be serialized, type information should be serialized statically, then now all of the requests to Elasticsearch will contain a $type information. So we got quite a few bug reports saying, hey, the call to Elasticsearch doesn't work, and then we found out they had a static JSON.NET configuration. And secondly is that the dependency on JSON.NET is every time a new major version came around for JSON.NET, we basically got two bug reports. One was, please update the major version for JSON.NET, which we then promptly did. And the second one was, hey, please don't update to the latest major version of JSON.NET yet, because my application is not ready. So in 6.x, we rethought how we actually wanted to expose a serializer to the user a bit. So the low-level client still, Elasticsearch serializer is still responsible for the whole request and response. But in the high-level client, the serializer that you inject is only used for certain user-defined types in the request and response. So for documents that are returned from a search call, for instance, or script values that are part of an aggregation. So only in specific parts of the request and response do we actually call out into your serializer, and for everywhere else we call our own serializer. So we've affectionately called this donut hole serialization, but it was quite a chore to get that implemented. The nice thing about this is that our internal serializers for request and responses are not something that you can touch anymore, so it doesn't, and no configuration will bleed. We still default to JSON.NET, but we've written tools to internalize and rename space JSON.NET into our DLL, so that we don't conflict with any JSON.NET in the Newtonsoft namespace that you might have in your application. And in 7.x, we took it even further, where both the high-level and low-level client now default to UTF-8 JSON, and both mainly for performance reasons, because we definitely saw a high performance and memory gain in terms of CPU and in memory when shifting to UTF-8 JSON. And because everything is now internal and abstracted, we have the freedom to switch out serializers as we see fit, and we'll more than likely intend to, over the course of 7.x, either we are definitely looking into the new system.text.json, maybe create a mix between UTF-8 JSON and spend JSON for that standard 2.1 once that ships later this year. So yeah, there's a lot of background to that Elasticsearch serializer. That's very handy to know if you go and dive into our code base. Yeah, so now I've mentioned things that should be expected and to have in the client. You can instantiate the client. The client will do connectivity bits and serialization and deserialization. But the client also has some bits that might be unexpected. So the first one is code generation. So we are able to generate part of our code based on a spec that Elasticsearch itself publishes. So if we look at the Elasticsearch repo itself, in REST API spec source main resources REST API spec API, there's a whole list of all of the APIs that Elasticsearch exposes, and they are documented in a custom JSON format. So here we have an API named search, a link to the documentation, the methods that it supports, and all of the URLs that are considered search, part of the search API. And then, so for instance, here we have the path underscore search, which searches everything in Elasticsearch, but you can also limit it to a certain index. And then this index part is documented here as a type of list, so you can specify multiple indices. Similarly, the query string parameters are documented. So any query string parameter that this API accepts is documented. But if we continue to scroll down, we see that there's no body or request spec as of yet in Elasticsearch. So the specification is great to generate the low-level clients, because remember, they don't really provide you with typed interfaces for the requests and responses. But for the typed APIs, they need to be manually maintained as of now. We're still actively looking into ways to automatically export these specifications from the server. So if I run the code generator, I'll wait for it to build. Building becomes a lot more fun with the nyancat plugin for Writer, I have to say. So, okay, so the first thing our code generator asks is, do you want to download these REST specifications? The default is no, because we download them and store them in our own Git repository as well. So here we have all of these files as well. So I'll just use the files that we have in our repository. The second question it asks is, do you want to generate code from the specification files from disk? So let's generate some code. So here it's list, like reading all of the files and creating a domain model of all of these specs. Now it's generating whatever it can based on that spec. So most of the low-level client is actually generated, apart from the connectivity bits, and a lot of the high-level client is generated as well. So if we now look to our repo, we can actually see that the only thing that has changed is the program that I just modified to showcase the client itself, but there's no actually code generated. But if so here we have a hard-coded list of APIs we are not quite ready yet to map, so we need to still map these APIs. So if I uncomment one of these and then run the code generator, wait for my nyancat to finish building, and again, don't download the REST specification and run with the specifications from disk. Wait for it to finish. We can see that, hopefully this is readable, that so we actually created request parameters for the freeze request. The low-level client has added methods for freeze, and it knows that the index is a required parameter based on the specification, so it's the first argument. But also in the high-level client nest, we're able to generate quite a bit. So we can generate part of the requests because we know the query strings. So we create a parser class for the descriptors and the request. Descriptors are for the fluent interface, and requests are for the more classical object initializers like C#. And we can even generate high-level client methods. Although, as we see, it's complaining right now that we haven't implemented freeze response yet, because that's something that we cannot generate. So we have to manually implement this now. So, yeah, so quite a few bits we can generate from the specifications as published, which is quite nice. Really helps bootstrap new APIs and changes in the spec as they come through from Elasticsearch. So if I now just undo the changes the code generator did, so that we can still build. We can actually look at how this code generator runs. And so we actually read the files and use the files and the C# code to create a domain model. And basically treat it as a website where we feed that domain model or view model to Razor files. So here for the request, we feed our domain model of API endpoints, which are the spec specification files, augmented with some more information from C#. And we basically feed it into Razor and generate code from that. So yeah, in the past, we really had to take care of white space so that the generated code still looked okay. But more recently, we shifted to using the old school code DOM, the compiler helpers that were there before Roslyn, to format the files. So if I look at the so we don't accept. This is a simple trick that we use to actually format the C# code in code. So we don't actually have to care much about indentation in the Razor files as well. So because the code will be formatted by C# syntax tree, which is part of the CodeDOM C# CodeDOM package. Yeah, so I'll move along to the next section. Which is the virtual cluster testing, which is a very cool feature that we have, and really showcases why having a highly injectable client is really, really useful. So I mentioned before, Elasticsearch can be 1 node, can be 100 node, can be in different topologies with different roles. How do we actually test against this, and how do we test against catastrophic failures? Obviously, integration tests are good to have, and we definitely do have them. But having integration tests for the 100 node scenarios or the 1,000 node scenarios are hard to maintain and run in terms of actual wall clock time. So what we have in the client is, I have to use my little cheat sheet. Have a virtual cluster implementation, which we can allows us to create a little state machine as to how to reply to responses. And this virtual cluster is really just an iConnection implementation. And so the only thing that we have to stop is the virtual cluster. All the other components are the actual real components that we use. We just don't use any I/O when we are calling this virtual cluster connection, because it's some type of in-memory connection. And anytime we call request, which is the only part of the interface, it will return a different response based on the state machine that we've set up in the test. And so this really allows us to do very complex things. For instance, here we set up a 10-node cluster where all of the API calls will fail, except on 9209, where it will always succeed. And then we basically can assert on the request. So we see a bad response, up until 92.08. This all happens as part of a single API call. So new client call represents basically represents one API call, such as high-level .search. And internally, that will actually do, I can find the file again, actually do multiple calls. They will try a call to 92.00, all the way up to 92.08, and then it will turn in a healthy response from 92.09. And then the user will just get back a healthy response from Elasticsearch. And the application doesn't need to know that we filled over, although all that information is returned and logged as well, of course. Yeah, we can use this little helper that we use to visualize it. If we run this test, and wait for 9 to finish. And while that's loading, I'll quickly move on to our next bit, which is is the fact that our tests are also our documentation, which is has been very, very helpful for us. I think it started running already. So it built in an exception, which is exactly what visualize calls does, but it will give us a visualization of what happens when you make two API calls on this current state. And here we see that the first API call, as was exhibited in the test, actually yielded a healthy response from 92.09. But the next time we call it, we won't retry any of the nodes that we know are down. We'll directly go to the one healthy node, which is 92.09. And these nodes won't be coming back until they're resurrected. In the interest of time, I'll skip along, but we can test many, many different aspects this way. We can shift time back and forward thanks to our time provider, and set up sniffing rules as well to return simulate network disconnects in the cluster itself, where it may be a possible split brain scenario. But the next thing I want to talk about is I have a little. This is not helpful. The magnifier just decided to come in play. So let me close the magnifier. Okay, I can actually type in the ID again. But what you actually see here is that we actually have quite extensive comments on our test. And the reason for that is that our tests are also our documentation. If you go to the elastic.co site, you can see that this test is actually also up on our documentation, and the text that you see here is the same text that exists in our code. And the cool thing is that actual code that we compile and test is also persisted in the documentation. And the documentation is in ASCII-doc. So if you click edit here, this is not helpful. Yeah, if we, I'm in an incognito mode, which is obviously not that handy here, but then we would see that this is actually backed by an ASCII-doc file. And the comments that we type here are actually also in ASCII-doc. ASCII-doc is a similar format as Markdown, but it's more geared towards building actual books and PDFs itself as well. The way we do this is by utilizing Roslyn to our advantage. So we actually use localizer to create a new project in memory based on the current Elasticsearch solution, and we add Elasticsearch.net, the low-level client, the high-level client, and the tests to this in-memory solution. Then we get the workspace. We need to add all of the documents to the workspace, which is kind of a little quirk with the new SDK project files. And then for each file that we deem a documentation file in the test folder, we try to save it to the documentation folder. And depending on what file type it is, we'll do a different thing. If I look at the different files that we have, you can see that we can put raw ASCII files, and they will just copy over verbatim, same with image files and documentation files. But the C# documentation file is interesting because here we actually read the C# file and use this doc converter to create the documentation box out of it. And this is what this doc converter does. It's actually get the AST from the document itself. Then, based on what kind of test it is, we use a different AST visitor and use that to actually find the interesting bits that we want to preserve as part of the documentation. And so here, we visit trivia. Yeah, and so trivia is basically all of the comments. We're only interested in this multi-line documentation comment trivia, which is a very underutilized feature in C#. So here, normally if you do a multi-line comment, it's only denoted by 1 star. But to Roslyn, the multi-line comment and the multi-line doc comment are technically 2 different things. So we utilize this little difference to make sure that only the parts that we actually want documented and are not multi-line comments will be part of the ASCII documentation. Moving on is our actual test itself. One of the interesting bits in our test framework is that we only have one test project, and it can be run in either an integration or a unit test mode. And so these are demarked with either a U attribute or an I attribute. That's a choice I made a long time ago, but I would still do single letter attributes as a topic for another discussion. But the fact that depending on how we run our tests, we can run them in integration or unit test mode is really, really helpful, because that means we can write many tests once and then decide how to run it later. So this is I'll do my little cheat sheet. So here, you can see that here we have a little test, which basically asserts that you can send from and slice to Elasticsearch. This search usage test based actually implements API integration test based, and it defines several unit tests. So here we have it's the correct URL. We don't actually need to go to Elasticsearch to know that we generated that URL. It uses the correct HTTP method, but again, it's something that we don't need to go to actual I/O for. But to know that the status code is correct and the expected the document is marked as valid as we expect it to, and the response is in the shape that we expect it to, we actually do need to go to Elasticsearch and do a proper integration test. So if we run this now, oh, that's the wrong one. If you only run the test from and size, it will only run the unit test mode, the unit test. And that's while that runs, I'll show the page that actually controls this. So we can see that the tests actually run. And only those 4 tests actually were selected. If we go to our configuration, we change this now to integration. Do it again. And run it again. You can see that it didn't actually pick up on our integration test. Sadly, this is something that sometimes works and sometimes doesn't work in Rider, depending on the release. So sadly, I need to make a slight modification build. Wait for it to fill, to run. And press run. Should select the integration test this time. Oh. Okay, demo docs are not on my site, it seems. Okay, well, sadly, the demo docs are not on my site. It's sadly the Rider ID doesn't want to pick it up. Usually it does pick them up, so I'll chalk that up to the demo docs and move along. So the reason that to actually facilitate this, we've built our own Elastic.xunit abstraction, which is a custom runner and framework for xunit. And the reasons that we did that was twofold. Basically, we want a lot of control on which tests we actually run and to reproduce, especially in integration tests. We don't actually want to run all of the integration tests if only a small portion fills. So we need really high granularity when filtering. And the second is that we need something that's called a high cluster fixture. So if we look at the form and size usage test and follow it to its base implementation, actually see that somewhere down the base class hierarchy, it expects something that's a high cluster fixture. And so if you're familiar with xunit, there are different fixtures that you can inject into test classes. So for instance, class fixture will be one instance shared for all of the tests in a class. And there's also something called a high collection fixture, which allows you to share state between multiple test classes. However, that and since we share unit test and integration test, if we want to run an integration test, we don't actually want all of these tests to run serially, because then the runtime of our test would be very high. So part of this Elastic.xunit, we've created this iCluster fixture, which we make sure gets instantiated once for all of the tests that depend on a particular cluster, and then the cluster is disposed at the end of it as well. And then to do that, we've also have a little project that's I'll show now. If I can type correctly, Elasticsearch, then hopefully we'll get there. And so in this Elasticsearch.net abstractions, we're actually building Elasticxunit, and to make sure that we can run Elasticsearch without actually polluting your system, we also have built a managed ephemeral version of Elasticsearch, and it's the one you see here as well. So this is very useful if you want to do integration testing against Elasticsearch. You can run Elasticsearch, and it will create all of the data paths in ephemeral folders, and as soon as it's shut down, it will also take care of removing all of the data as well. So yeah, if I have to rebuild this now, I would maybe use Docker, but this was a build before Docker was actually feasible on Windows itself. I see that the time is running out on me. There's a lot of things that I wanted to showcase as well in terms of build automation, which I'll briefly touch on. So Elastic's our build is an F# project running Bullseye and Fake, and then mixture together to actually run all of our build. And the reason that we've chosen this setup is that we actually want to do a lot more things than just that MS Build provide us. So for instance, when we build NuGet packages, we actually unpack the NuGet package and go over every DLL that's part of that NuGet package and assert that the version numbers are correct and that the signing key and in turn the identity of the DLLs are correct. And furthermore, we have a lot of different toolings in here. We can generate release notes, a very nice benchmarking setup where we can run benchmark.net tests and publish the results in to Elasticsearch, which I ran out of time to showcase as well. So yeah, I think in the interest of time, I'll leave it at this. I do want to showcase my last slide. Thank you for sticking around. There's quite a few different .NET related GitHub repositories if you're interested in Elasticsearch or Elastic and anything that has to do with .NET. Obviously, we have the client itself, which lives in Elasticsearch net. Elasticsearch itself is worth the browse through. There's specification files and also test files there that are handy to read. We have a fully blown example repository that builds a new search application, a NuGet gallery application as well. So if you want to learn Elasticsearch and .NET, I would highly recommend trying out the Elasticsearch net example. And we basically walk you through start to finish how to build and run Elasticsearch, do mappings, we built completion suggesters. So really try that out if you're completely new to Elasticsearch. And then this abstractions repo is if you're interested in our ephemeral Elasticsearch that can be run without leaving traces on your machine. Check that out as well. Or if you want to run integration tests against Elasticsearch, you can reuse our elastic.xunit framework as well. Yeah, and furthermore, we have a couple of different toolings that we built as a team under Nolian. So we have an assembly differ, which we use to make sure that we don't introduce breaking changes as part of a release. This is built on top of the just assembly by Telerik, but we extended it to make sure that it can download DLLs from NuGet, etc. as well. And then we have the assembly rewriter, which is what we use to internalize dependencies, which is a very, very handy tool. So not only does it internalize dependencies like IO repack or IO merge would do, you'll also rewrite all of the types of that dependency into a new namespace and make them internal. So it really hides any dependencies that you have. Whether that's always good practice, I will definitely not recommend it to do for all of your dependencies. But if you maintain a library and you want to don't deal with diamond versioning conflicts, then this is definitely a very, very handy tool to use. And we plan to ship this as a .NET tool at some point in the future as well. And the other two things that are the other interesting bit that we haven't showcased is in the abstraction repo. which is the benchmark.net exporter, which we really want to publish as well this year, so that you can run benchmark.net on your CI, but have it published results in Elasticsearch, and then you can plot your performance over time as well. And lastly, but not least, is that we also building the APM agent. It's a dedicated team in Elastic. If I find my slides again. So if you want to look at the pre-releases for the APM agent for .NET, have a look at elastic/apm-agent.net. And yeah, this is the time to really provide feedback and steer where that project is going as well. So with that, I would like to thank everybody for attending. And
all right, thank you, Martijn.
Yeah.
I'm checking the questions. There's actually one nice comment about using the Nyan progress bar. We'll find that interesting. Also got a question if you could share your slides afterwards. So if you can share them with me, we'll publish them if you're okay with that.
Absolutely.
And with that, I'll quickly jump over to my screen so we can show a couple of resources where people will be able to find the recording and so on afterwards. So if all is well, you should be able to see my screen. If you want to learn more about Rider, you can do so on our website. We also have Twitter, where we also just posted a tweet showcasing the Nyan progress bar in case you're interested. We have our blog. That's the one where we will also publish the recorded webinar afterwards. And of course, Martijn is on Twitter. He has a blog as well, so feel free to check that one as well. With that, thank you for joining. Thanks for spending the time with us. And yeah, check our other screencasts on JetBrains TV and make sure to check the recording afterwards. Thank you.